get started.
Okay, so if you can hear me, I'm Ilaria Pascucci, hi, and it's my pleasure to introduce today's speaker, Luigi Zallio. Luigi is a second-year graduate student at the University of Milan, but is actually also spending time at the European Southern Observatory in Munich. His primary advisor is Giovanni Rosotti, but is also co-supervised by Miguel Bione. And he's going to tell us also some new interesting results on the DECO Large Program. So yeah, please take it away.
Right, so thank you, Ilaria, for the introduction. Yeah, I'm Luigi Zallio. My main supervisor in Milan is Giovanni Rosotti, and Miguel Bione is my co-supervisor. And while I'm at ISO, I'm supervised by Anna Metello. So yeah, today I will be talking about some general consideration when it comes to measuring proto-planetary gas physical properties in general, in particular gas disk sizes, and I will show you some preliminary results from the ALMA DECO Large Program. So just before starting, I wanted to give you a brief sum up of my 1.5 years of PhD. So yeah, I started my PhD in Milan, and I started with a theoretical project that I will be telling you about more towards the end of the talk. And right after that, I started developing a code to fit the visibilities of proto-planetary disks, and it is called CSALT, and I'm doing this with Sean Andrews and Richard Teague in particular. And then I joined the ALMA DECO Large Program, which is composed of 80 proto-planetary disks. I will tell you more about it later. And my goal is to extract gas disk sizes, but then we figured out that we could do a little bit more than that. And so I will tell you about it. And then I started a follow-up project on the upper scope, start from the region. And yeah, since September, I'm at ISO, as we already said, and I will be staying there until the end of August 2025. My PhD until now has been very technical. Most of it has been very technical because I'm into software development and also very much related to ALMA and visibility stuff. So I try to, let's say, do this presentation in a very simple way, simplistic way. So basically, it will be very general and introductory so that everyone can follow this. So basically, the goal in radio astronomy is to map the sky brightness distribution of our sources. And in particular, we want to understand the angular distribution of each of our sources. So the requirement for this is to resolve the emission of the sources. Okay, and what do I mean by resolve? So here I put an image of what I consider an unresolved emission, barely resolved emission. So basically, all of the surface brightness can be covered by just one beam. Okay. While a resolved emission, you can see the beam right down here in a white point, and well, basically you can fit several beams inside of the brightness distribution of the source. Okay, so what are the difficulties connected to this? Well, first, the emission is very weak. So just to give some numbers, the strongest radio source is a 1 watt in a bandwidth of 1 gigahertz. Okay, and also the emission is quite compact usually. Because so the typical angular scale for proto-planetary disk is the arc second. Okay, 1 arc second is the angular width of a €1 coin, which is I think similar to 50 cent USD dollars at the 5 kilometer distance, which is 3-point-something miles. So it is very narrow. So we need to use telescopes, of course, but also here to obtain a 1 arc second resolution at a wavelength of 21 centimeters, we will need a single antenna of like more than 40 kilometers diameter. Okay, while the largest existing antenna on Earth is the Green Bank one, and I don't think it's going to be ever matched by anything else. So the only technique that allows us to achieve our goals is radio interferometry, is interferometry in general. And what is interferometry? It is the coherent summation of voltages from separated antennas. Okay, and when we sum up all of the voltages, we call this operation correlation. And here I am adapting some slides from Rick Early that I found this lecture 1 year ago at the VLA school in Cornell. So basically, how does a correlator work? We have 2 antennas here, 1 and 2, and they're pointing towards a distant source. And basically, the coherent radiation is reaching out the antennas with a geometrical time delay. Okay, so basically, each antenna produces a voltage output as a sinusoidal function, and basically these outputs are then multiplied and averaged to produce a cosinusoidal response function. Okay. And basically, for an extended source, the voltage output is simply the integration of the solid angle of the electric field. So when you average together, do an exchange of integrals, and basically you come up with this nice relation that relates the output of the correlator with the surface brightness distribution that we're interested in. Now, well, basically, if this is in the form of a cosinusoidal function, okay, because you have an integral, and if you have an odd symmetry, then your correlator is completely invisible, completely blind to that component. Okay, so what we actually do inside of the correlators is that we add a phase shift of 90 degrees, which becomes basically a sinusoidal function. Okay, so that in the end, from each pair of antenna, we get both the cosinusoidal and the sinusoidal function response, and we sum up them together to create this visibility, which is something that we define, and it is a complex number. It takes into consideration the cosinusoidal and the sinusoidal part of our emission. Okay, so then in the end, we are left with this fantastic relation, which is the visibilities are related to the surface brightness distribution of our source through a two-dimensional Fourier transform. Okay. Now, what do I do with these visibilities? Well, basically, the goal of my PhD is to take them and to do science without further processing them. Okay, so without using images. Is this easy? Well, I will say not at all, because it is very complex. It is very difficult to think in complex space. Okay, so I did put an image that I generated yesterday. This is a two-dimensional fast Fourier transform of an image. Can you guess what it is? I don't think so. It is the Fourier transform of a saguaro. And this is a nice picture that we took together with some friends in the last days. So yeah, it is very difficult to correctly understand what the visibilities are, right? And what they are telling us. So more about interferometry. We can use compact configurations of our antennas, and we can get as a response basically some very like the total flux component of our bright sources, okay, of our plane sources, sorry. And well, if instead we put some antennas in the outer edges of our configurations, so we have the long baselines, the so-called long baselines. Well, we lose a part of the total flux, but we gain in details. Okay, so this is how basically our ALMA antennas would work, and the different configurations. And now, once we have the visibilities for our observation, we usually do process these visibilities through the cleaning, which is basically an inverse to the Fourier transform, in order to produce the images. That I is the surface brightness distribution in the real space. So this procedure is really amazing, but it relies on the convolution algorithm, such as the clean, and it needs a threshold to stop. So basically, the result is that, well, depending on the user, it could give different results, okay, because you can set different weights. And it also introduces systematics. So basically, the thermal noise is Gaussian in the visibility space, but once you get your image, it is not Gaussian. Like each single pixel is correlated with the others. Okay, so you should take that into consideration for previous images. So that's the point of doing all of our analysis using visibilities. So let's jump into the first part. So this is what I've been doing since in the last 1.5 years, basically, working together with Sean and Richard. So basically, we are creating this nice tool, which is called CSALT, Stellar Spectral Analysis with Line Tomography. And basically, you can analyze the morphological emission, the surface brightness emission of spectral line. Okay, so CO, whatever line you prefer. Okay, and directly using visibilities. And how does this procedure work? Where first of all, you have to create a model. So once you have your parametric prescription for a model for the disk emission for the disk surface brightness, well, then you generate it, you create it, and it is of course dependent on the frequency. Okay, so you create a cube, and once you have the cube, you read the UV points of your MS file, the original data that you have, and you basically just fast Fourier transform your cube into all of the UV points. Okay, and this is the first step. Now, the second step is the second and third step. I would say the third and fourth step. Sorry, they are more related to the spectral dependency component of your observations. Okay. So first of all, you want to do a correct Doppler correction. Okay, an exact Doppler correction. And yeah, I will not get into the details of this. You can ask more questions on it, but it's not trivial at all, especially with ALMA. And once you have done your Doppler correction, then you want also to take into consideration the Hamming kernel, okay, so the windowing function that the correlator of ALMA does and applies to your original data, okay. So we do take this into consideration so that we have apples with apples. And not only this, but we also take into consideration the fact that after you apply your Hamming smoothing, okay, well, then you have a correlation among nearby channels in frequency. So we also include this because the correlation matrices are known, and we include it in the evaluation process of, you know, the model MS file that you want to compare with the original MS file. Once you have done everything, like all of this, you are left with a final cube that you can then insert inside of an MC chain inference procedure. Okay, for example, using MC or any of your desired samplers. And once you have run your inference procedure, you can obtain the posterior distribution function for your chosen model. Okay. So in the end, you're left with the best combination of parameters to reproduce the cube morphology, the original cube morphology. Okay. So a part of my PhD, in a part of my PhD, I developed a nice model that takes into consideration like the disk geometry, inclination, position, angle, offsets with respect to the center of the image, and then also the systemic velocity. Then we included, well, of course, the stellar mass, and then just using a Keplerian mass for this, like a Keplerian stellar mass. You can also include like a small deviation, like Brech's gradients, and whatever you want, but it complicates a lot the model. Then I have a brightness temperature profile in the form of power law, and everything works. Then I'm mimicking an optical depth profile, choosing an exponentially tapered power law. And also, of course, the disk emission is flared, okay, depending on different molecules, molecular tracers. So, well, I've used an exponentially tapered power in every previous works again. So when you combine all of these parameters together, it's 16 in total. You can get the projector surface brightness profile, which is optimizing your well, parameter, your emission, your brightness emission. And this is what I'm doing for the ALMA DECO Large Program. Okay, so let's jump into this. If you don't have any questions on what I've said until now. Perfect. So let's go on. This is DECO. So it is a collection of 80 disks around low mass stars. The PIs are listed here: Ilse Cleeves, Anna Vitello, Dan Anderson, Yuri Aikawa, and Vivian Guzman. And it's a collection of 80 disks, as I was saying, in 4 different star forming regions: Ophiuchus, Lupus, Taurus, and Camino 1, which is very nice because we can get like different ages, okay, for each of our protoplanet disks. And it is a moderate resolution observations of molecules. So this is because it is a chemistry large program, so we don't necessarily want to resolve completely like detailed resolving the disk emission. And the main goal of the program is to compare the disk chemistry to the composition of exoplanet atmospheres to understand the planet formation processes. So this is a nice collection of the 80 disks in the continuum, and you can see that the beam, as I told you, is not the best, but still we can resolve the emission of most of our disks. So I'm very happy with it. And here I put this nice slide just to point out. I've adapted this from a presentation of Ilse, and I just wanted to point out that, well, basically most of our observations are usually biased towards the very bright and big disks, okay, because those are the disks, of course, that you can resolve better and that you can characterize better. But what about the typical disks, such as the ones that I just showed you? Like, can we get precise measurements of disk physical properties also for these typical disks? Well, with visibility fitting, as I'm going to show you now, yes, we do. Yes, we can. So yeah, let's show you some early results. Okay, so this is a well-behaved source. I will also show you some more complicated examples. So just to refresh your mind, I'm fitting for the disk geometry, Keplerian stellar mass, a lower low for the temperature profile and optical depth profile, and also the vertical height. And here in this plot, you can see on the first row the data. So this means that I took the MS file, the original MS file, and I'm imaging once I set a certain channel width. Okay, so these are all of the channel marks of the disk emission. Now this is the model, the image model. So this, in order to get this, I created an MS file equivalent to the one of the data, okay, like exactly equivalent, but with my parametric prescription inside of it, after the optimization through the NCMC procedure that I told you about. And this is the morphological emission that I can obtain after the cleaning. So these are data model, and here are the residuals. So I created an MS file of the subtraction of the model from the data, and I imaged it. And here I'm showing you in with contours the 3 sigma and 5 sigma contours, and there are no 3 sigma and 5 sigma contours. Okay, so this is a very good fit. Okay, and most of my fits have no residuals at all.
Sorry, just to clarify, so this is just for visualization, but the best fit is found in the visibility.
Absolutely, yeah. This is just for like as a final check. Yeah.
What about that? So for such data quality, I mean the resolution compared to the size of the emission, can you really constrain the Z over the frame structure?
Well, of course you have some generacies. Of course you have the generacies because yeah, you have the generacies, but yeah, you can do it like also pretty well. Like as I'm going to show you in a few slides, you can also like I have some examples where I could track the vertical height of both 12CO, 13CO, and eventually also CAT, but I think I'm not showing that. And you can clearly see that yeah, it's comparable with the expectations. So yeah.
But I mean, this is very small compared to the beam size, so it's very challenging.
Yeah. The point of doing this in the visibility space is also that, well, you basically, if you did this operation in the image plane, you will use the beam of the cleaning, right? So you can get basically some higher angular resolution with respect to the ones that you get in the image plane using visibilities. It's not huge, a huge improvement, but it's still something. Yeah. Yeah, so I usually like to say that we are seeing the unseen basically with very resolved observation and get like some very nice complete descriptions of our disk. So once we have the best combination of parameters, well, the first goal would be to perform the gas disk radii extraction. Okay, so basically I compute the surface brightness profile at a certain frequency in particular. This is for the 12CO, so I use the rest frequency of the 12CO, and I integrate it to extract the radii of 68%, 90%, and 95% of flux, total flux. And the main scope for this, like the main goal, is to prove the proto-planetary disk evolution scenario, in particular MHD winds against viscous scenario, because as I told you, we have 4 different transforming regions, so we can clearly see, in principle, we should be able to see any trends of disk evolution with age. Now the second goal, yeah, is what I was talking about. The second goal is to extract the vertical heights. Okay, so basically simply from as a direct, this is just a direct measurement from the fit. Okay, so I can plot the vertical heights and understand the stratification of, for example, different CO isotopologues. And also here the main scope is to study the gas evolution in proto-planetary disks, study the thermal structure, study the stratification in general, and the disk, and the disk, each single disk. And yeah, some connected goals. This one is very, I think it is also very connected to what Bingshan is doing. So I'm also very looking forward to having more chats with about this. Sorry. Yeah, connected goals, additional connected goals is that, well, of course, I will be collecting a lot of geometrical parameters, and usually, I mean, due to the fact that the gas emission is more extended than the dust emission, well, we believe that the inclinations and position angles that you get from the gas are more accurate than the one from the dust, and they are also less inclined to be degenerate in terms of the position angle and the inclination. So this is going to be very interesting. Then, yeah, of course, I will be extracting 12CO, 13CO, and CAT fluxes once we get the correct Capillary masks. and study in particular the correlation between the flux and the radius in different star-forming regions. You will see a strong connection with your work. Yeah. Then I will provide a collection of dynamical masses and also study how R gas over R dust evolves in different star-forming regions. So there is a lot of things that will come out of this, of this work.
What is the expectation on the second one?
Yeah, I don't know how it should evolve as a function of time. I'm really not sure about that. But in principle, yeah, I mean, it would be interesting also to not see any evolution, because it will simply mean that, as we already know, as we already expect, like the most like the more the disk is extended, then the biggest, the highest the flux is, right? So the expectation is that as a star-forming region is older and older, then its disks should be shrinking, maybe as a function. So we should see maybe these kind of things. Yeah, but it depends on the evolutionary scenario that you trust the most. So until now I've showed you some very nice images and some very nice examples, but some of the sources, actually many of the sources, are quite messy. So here you see an example. This is some like a handful of well-behaved channel maps. Then all of a sudden you have a cloud absorption, so a foreground cloud which is absorbing completely the disk emission, and then all of a sudden you have a huge cloud emission which is completely shadowing the actual disk emission. So how do we deal with these sources? Well, we basically added a switch inside of CSALT that allows you to not take into consideration the contaminated channel maps. Okay, so basically these are shadowed because I'm not taking them into consideration, and I'm just evaluating my likelihood on the first handful of channels. Okay, and as you can see, I mean, you can get a nice description of how a proto-planetary disk will look like if we just take into consideration this wing of emission. Okay, so the clearly well-behaved ones, and this is the most that we can do actually.
I ask a question.
Yeah.
How do we know those are cloud emission instead of the emission from the disk themselves?
Like, you mean this part here?
Yeah.
Well, because here I'm just showing you maybe a small portion of it, but you can clearly see from the large picture, like the whole cloud, it's a huge.
And maybe another question is like for the well-behaved disk number 3, maybe why in the last panel should be the residual in the bottom, but why for the well-behaved disk the residual looks still like quite significant? So it seems like data and the model not really assistant.
Yeah, you mean, for example, here you have this very red knob. That's the cloud that starts being evident. Yeah, in particular, every time that you see, like, for example, here, a blue residual, that means that the model is brighter than the data. And in this case, it's a combination of the two of them, because here the disk is starting to be absorbed. Okay, so this is why you see this very blue dot. Okay, but at the same time, you also have some cloud emission. So this is the diffuse cloud. Yeah, so in this case, for this particular disk, it is clearly it is fundamental also to check this kind of plots, because you can clearly distinguish them cloud from the disk, and you can interpret the results. But the corner plots always look quite converged also for this kind of sources and results. So this is what I just told you, so I'm gonna skip. I also wanted to show you this type of sources. Maybe you can guess which star-forming region this is.
Lucas.
Yeah. So basically, here we see at the beginning a very nice and again well-behaved emission from the disk. Then mass absorption, mass again, and then we see a different disk, like with a different PA with respect to the beginning, to the one in the beginning. Okay, so this must be a binary probably. Okay, this should be a binary with also cloud contamination, etc. These are very difficult to treat as disks, but somehow doing the correct cuts, as I was telling you before, and considering specific portions of the spectra, we can still extract something. We are still able to use. Sorry.
It's like DECO wind panels. Is that right?
You mean, yeah, this diffuse emission, it might be, yeah, it might be, yeah, it might be, yeah. And like in these cases, we can also use isotopologues to go deeper. Right? So for example, here in the 13th CO, the binary emission disappears. Okay, so it's too faint to be detected. But for example, in the first part, in the first disk, you can see that it is well behaved until the systemic velocity at least. So we can get more constraints in the disk emission. Okay? And we can also go to the C18O, but it is very faint. And of course, for the binary companion, it disappears. But here we have still some emission, maybe using a different prescription, like a very simpler one. Like, for example, just taking into consideration the mid-plane emission instead of the vertical heights, we can still get something out of this. But we can also use different tracers, like 12CS, which are very bright for some of the power sources. And yeah, do you have any questions before I move on here? Because otherwise I can, yeah, I will move on. And I wanted to leave you with this pedagogical slide. So this is a tool that I developed because we were having troubles with the calibration. Okay, and so basically to inspect the visibilities, this is a nice way to visualize actually how your data will look like in the Fourier space. Okay, so this is the average real part of your visibilities, and basically it is a function of the channel. Okay, so the channels are moving, so this is in frequency space, and as you can see, this when it starts to be diffused, okay, this is the beginning of the emission. Then this is the systemic velocity when it's an X, and then it goes towards the other peak of emission. And this is very interesting. I feel like this is very pedagogical. I was very happy, and it helped us. It truly helped us solving our problems. So if you want to take a look at it, it's on my GitHub. And yeah, so I will pause the DECO part now, and I will move towards the next project. Hopefully it will be published by the end of the summer. So basically this will be a follow-up of the paper that just came out from John Carpenter at the beginning of 2025, where he published this huge amount of data. So 202 sources, 120 of them are detected in the continuum, and 83 are detected in the 12th CO. And then talk about the upper suppository region, if I didn't say that. And it is a collection of cycle 0, 2, and 6.7 continuum observation with mild angular resolution observations. And it's like 2 or 3 minutes per source. So it's the integration time is not much. And this is a very nice complementary data set with respect to DECO because upper score is the only star forming region which is not covered by DECO. Okay, so this is a very interesting work to do as a follow-up of DECO or follow before. So the goals are the same for this paper are the same that I just told you about for the DECO Large Program. And in particular, since among the 83 5 sigma detection in 12 CO, 33 are bright and resolved, then I will be using the same DECO model. But for the others, like the 50 ones, I have developed a new CP model that I'm going to show you in a few seconds. So this is how the bright resolved disks look like. Okay. Like I'm actually amazed because this is 3 minutes integration per source. Like it's actually fantastic. And while, for example, faint and compact disks, we have these tiny blobs. Okay, so it's pointless to try to extract the vertical heights for these objects. It's totally nonsensical, and also the fields don't converge because I tried. So basically, we developed a new model, which is I'm still well, of course, I'm still fitting for the this geometry, even if we know that there are huge degeneracies between the inclination, position, angle, and mass, for example, for these sources. Then I'm still using the Keplerian mass temperature profile, and I'm just assuming mid-plane emission. So I'm just fitting for an outer radius. Okay. And this is for these sources, this is the only reasonable, like the only parameter that I actually completely trust. Because all of the others are extremely degenerate, the ones in others. So yeah. The big picture is that we will collect in total 80. I will collect 80 gas disk sizes, 20 per star forming region using DECO, and then 83 gas disk sizes from upper Scorpius through this work. So what are the consequences of having a nice, like a robust and uniform description of your sizes, gas disk sizes? Well, it's that we can then perform accurate population synthesis models to constrain the accretion scenarios of our proto-planetary disks. And in particular, we can put empirical constraints on the relevance of emission winds, viscous accretion, and the internal and external for the population. And this is also going to be in the second wave of DECO, which apparently is going to be led by ALMA. Yeah, so I will move towards the last part of my talk if there are no questions.
I have a question. Yeah. So how long does it take to run one model for the fitting cubes?
Yeah, so it depends. That's a nice question. It depends on the data, first of all. So it depends because, well, of course, if you have high spectral resolution, like in DECO, so 80 meters per second, sort of, well, then your likelihood evaluation scales linearly with the number of channels that you consider. But also, like the amount of pixels that you choose influences that, because it scales as like 2n log n in terms of pixel number. So I would say that for DECO, in one day, running on like 15 cores, 15 CPUs, you can get a full constraint, like fully converged parametric description, yeah.
Sorry, one day
One
one
day.
object?
Oh,
One day, yeah. Well, in setting underscore, it's like 6 hours because it's, yeah, it's very shallow observation, so you have less pointers. But if you have like 500 cores, then you can get like the whole 80 disks in 1 week.
I'm also curious about the fitting themselves. So what are the parameters that are most likely to be degenerated to each other?
Yeah, well, if you have a if you have a resolved disk emission, for example, you get rid of the degeneracy, which is the main one between the inclination and the mass of the star. That is the main one. Then you still have a degeneracy between the temperature and the vertical, the vertical height and in general the vertical extent. But if the disk is resolved, you can absolutely trust the results. As the disk moves to be compact, you have to start not trusting the result anymore and just be, as I told you before, you can just start trusting the outer radius. That's it. Yeah. But I'm in the papers. I'm also providing some, I'm also doing MC4 simulations and testing how the fit scales in a good or bad way with respect to angular resolution, spectral resolution, and also different other degeneracies that are clear in disks, such as the inclination mass ones.
Yeah, but I think most of them are famous targets, so they have high resolution continuum data in the past. So you already have a good handle on inclination. Yeah, you can use those as priors.
Yeah, that's for sure. Yeah, that's what we are actually. Yeah, that's what we are doing, and I think it's a good point to use those values as priors, and then also say, okay, we can basically benchmark our procedure using those well-resolved sources, right? Like, it's trustable or is it less trustable? This is what we are also for the very extended ones.
What are the selection criteria for DECO?
So it was stellar mass, first of all. So GKM stars, 0.2, 1.5 solar masses. Then it was the accretion. So I think we also selected low accretors in general. And yeah, these two are the main ones.
Why only focus on low accretors?
I'm not sure. I'm not sure.
So it's different than the previous observations, I guess.
And so very quickly, the last part of the talk, I would like to dedicate it to this paper that I published during last year. So basically, it is called the emergence of the correlation between the mass of the disk and the accretion rate, mass accretion rate onto the central star, MAC, in the magnetohydrodynamical wind scenario. And it takes the hint from this nice paper of Carlo Manara in 2016, where he discovered the existence of this relation in particular for the Lupus forming region. finding a slope, like a correlation in the form of a power law with a slope similar to one, and also a connected spread. And well, there are also other famous correlations. You can see some references here for similar studies on these correlations. I will put them here. Basically, the main question of my paper is if we can explain the existence of this correlation using evolutionary models, and in particular, the magnetohydrodynamical models, evolutionary models. So so I give you here a very brief and general overview of the two main accretion scenarios that are in existence in a protoplanetary disk evolution. And they are the viscous accretion, where basically through a redistribution of angular momentum, the disk enlarges with time and it becomes thinner and thinner. And it is usually coupled with internal and or external fluid evaporation to actually kill the emission of the disk after some years. Okay, otherwise it will just become infinitely thin and infinitely large. And then you have an NHD wind-driven accretion, where basically angular momentum is now ejected from a magnetohydrodynamic wind because the disk is ionized. Okay, and well, you lose angular momentum and also mass. So in the end, your disk shrinks with time instead of enlarging. So basically, the correlation between the mass accretion rate and the mass of the disk has been studied throughout the years, and in particular in 2017, Lodato and Rosotti et al. 2017, they showed that basically the correlation can be naturally derived in the viscous scenario. The problem with this is that the viscous accretion, the viscous evolution cannot explain the spread. It can explain the slope, but not the observed spread. Okay? Because as you can see here, basically after 10 mega years, there is no spread anymore. Okay? The correlation is just 1-to-1, with slope of 1. So there have, after some years, Tavon in 2022, well, he published a letter saying that MHD winds can reduce both slope and spread of the MD M dot star correlation. And but it was not clear in that letter whether the result was relying on specific initial conditions or if it was general. So this is the angle of my paper. Okay, is it a general result, or does it need like specific initial conditions? And in order to do that, well, I started performing some population synthesis models. Okay, and in particular, the first result of the paper is that we understood which are the fundamental parameters to actually be able to see the correlation in the M dot star plane. And the fundamental parameters turn out to be spreads. Okay, in particular, the spread on the initial masses of the population and the spread on the initial accretion timescales. And where the initial accretion timescale is just the timescale of it describes how fast the disk is evolving. Okay, and so we provided a general rule of thumb that, as you can see here, I'm varying the spread on the initial masses, and if I increase it, we pass from this, which is a sort of if you're an expert of the field, it is called an isochronal. And then if we increase the sigma m0, we start seeing a population which could be fitted by a single power. Okay, so and the general rule of thumb is that the ratio of these spreads must be bigger than 1. Then I performed this kind of plot, and each pixel here is basically the result of the fitting of a different population of disks. So each pixel is a population of disks with a specific sigma m0 and spread on the initial accretion timescales. And after getting the population, I did fit it with a power law, and I could get both the slope of the power law and the spread of the correlation. And I'm just highlighting with these two colors the results that are in agreement with the results of Carlo Manara in 2016. Okay, and as you can see, there is a whole box of values for sigma m0 and sigma tx0 that can explain the MDM correlation. So there is no need of talking to initial conditions, but there is a range of initial conditions that can reproduce that correlation, the observed correlation. So moving on, I've also derived an equation for the spread of the accretion timescale, and it works very well for Young-style regions. Okay, it has the assumption that the accretion timescale has a Gaussian group normal distribution. So this is why for older star-forming regions it doesn't work anymore, because if you assume a Gaussian distribution and you let it fall, well, basically at a certain time you lose part of your disks, so the distribution is not Gaussian anymore, and so this analytical formula doesn't work anymore. But for young star-forming regions, it is quite accurate. And then we also introduced a correlation between the initial masses of disks and the initial accretion timescales in the form of power law. And basically the first thing was that we can still reproduce the correlation between the initial between the mass of the disk and the mass accretion rate by tuning by the exponent and the spread in the initial masses. And in order to understand whether we were biasing ourselves again by choosing specific initial conditions, well, first we derived some analytical slopes, so analytical solution for the slopes in the initial and final the condition of the population. And then also we produced again this kind of plot where you can see that there is a huge degeneracy between the spread in initial masses and the exponent. But again, the takeaway is that there is quite a range of initial conditions that can explain the correlation in spread. Okay, and also this kind of analysis I think is quite interesting because a posteriori you can derive the expected initial parameters that are determining the fact that you're observing a certain slope with a certain spread. So I think it's a very nice and interesting type of analysis that can be used again. So my conclusions. So the first one is that visibility fitting rocks, because we can provide a robust parametric inference. It avoids decline, as I told you, and it is, I think, currently the most complete way to analyze spectral line data, even if it's quite complicated. Yeah. And the second one is that stay tuned, the DECO's first wave should arrive in late 2025. And as I told you, I will provide a collection of geometries, sizes, vertical heights, dynamical masses, etc. And the main question is how these parameters evolve with age. And then also expectation is late summer, the upper scope paper is coming soon, and also CSALT is about to be published. If I have one more minute, exactly one. Yeah, I would just like to mention these a couple of additional projects that I'm working on related to the high mass star community. In particular, I would like to expand, well, basically the analysis that I told you about invisibility fitting also to Herbig disks. Okay, so basically I'm taking the complete sample of published in Lucas et al. 2024. And well, the main goal there would be to, well, try to understand how the vertical heights of class 1 Herbigs and the class 2 Herbigs compare, okay, and also provide some dynamical mass measures for these very massive stars, and of course again the size and ratios between R gas and R gas. And then during this summer, I'm hiring a student through ISO to work on this nice project, which is called Study on the Rotation of Water around the proto-black hole. The proto-black hole is a market strategy. But actually this is a 30 to up to 50 solar masses star. It's called G17. The data have been published by Luke Mode et al. In 2019. And basically the goal is to fit the maser of the water, which is clearly orbiting in a Keplerian way around this huge star. And well, the goal is to try to constrain its dynamical mass in a more precise way, because right now it's like 40 plus minus 15 solar masses. You know, it's very difficult to understand which is the mass of these very massive objects. So this is going to be a very interesting project. And with these, I thank you for your attention, and I'm available for any questions.
So maybe let's start in the room. Any questions? There we go. I can start. Can you tell us a bit more about some predictions of your model that fits the correlation between the disk mass and the mass accretion rate? What would you?
Yeah, you mean what I was meaning here is that Well, basically, once you have this kind of plots, okay, for example, let's focus on this one. Well, then you can say, first of all, for example, if a reasonable correlation between the initial masses of disks and the initial accretion timescale exists, how will it look like? Like from this type of plot, we can completely rule out the fact that the exponent is bigger than 1. Okay, so M0 cannot be proportional to Tx0 with an exponent bigger than 1. And this is already a huge prediction, right?
But the M0 would be which type of object would you choose? Is it class 1? Is it
well, yeah, let's say class 2s, yeah. And so it should be more likely, it is more likely to be a negative exponent, for example. Okay, so an inverse correlation. This is the type of predictions that I'm meaning. Like this kind of, so we could also produce this type of plots, and I do it in the paper for other parameters, okay? And you can, yeah, basically try to constrain the parameter space, which is allowing the observations that we see, okay? And this is why I was saying is a nice way to, yeah, try to interpret the initial conditions of our these populations by looking at the consequences, right? By looking at these correlations. And there is a guy now in Milan doing some follow-ups of these works. It's called Lorenzo Malanga. He's a new PhD student of Giovanni. Please go ahead.
Yeah, sorry, I think you said it, but maybe it went by a bit fast for me. Can you say again how you treat stellar mass in your visibility fitting?
Yeah, so I just choose a Keplerian profile, okay, for it. Of course, it's a Keplerian profile depending on the vertical height, okay. Because otherwise,
But given the assumption of a Keplerian profile, you're fitting for a stellar mass.
yes.
Okay, and do you think it matters that you're not taking into account the pressure?
So for the type of observations that we have, no.
Okay, because the resolution is just too low?
Yeah.
Okay.
Definitely, yes.
I guess I wonder, I guess it seems like the temperature profile is built into the model, so it seems like that it's, you have the correction in there already effectively, you've just decided not to put it in?
So I mean, I also have the prescription for with the pressure gradient.
It doesn't matter, yeah, okay.
It just like those parameters just.
Yeah, I can't imagine it doesn't, and are there any cases where you found something discrepant with the literature values for the reported stellar mass in a significant way?
So yeah, in DECO no, but in upper score, yes, I did. I'm like it's one of the most challenging parts of that paper. So I didn't put the plot, but typically I'm predicting some. So usually CSALT is predicting slightly less massive stars, I would say, with respect to the isochrone fitting.
But
Yes, massive.
but that's not, but I mean, it doesn't mean that's not a bad thing, right? I mean, that's,
I don't remember if it's less massive.
okay,
And
but,
there is a discrepancy.
and it's systematic.
It is,
Interesting.
in some cases, it is systematic. In some other cases, I think the like this procedure is not reliable enough to assess correctly the mass of the star, because if it is completely unresolved, then you don't know if you see just 3 channel maps of emission, because the disk is not inclined, or it is just not, the star is just not massive. So there is a huge degeneracy between
Okay,
those two parameters.
and in terms of so Valarian, you guys can remind me, is Upper Sco the region where the ages are all messed up?
Yeah.
So it's not maybe crazy.
It's not.
And also, I mean, like, so we should just throw out isochrone masses, we should just do this for everything, right?
Yeah, I think so.
Okay,
But yeah, and also, I mean, the isochrone fitting is really reliable on the. It really depends on the model that you're fitting for on those
Right.
isochrones.
right, no, I mean, this is great to have, basically dynamical mass measurements for 80 stars, this
Yeah.
is,
I mean, that's the point. I want to provide like a big collection of dynamical mass and say this is it.
and And in terms of, right, you mentioned that the original sources were chosen to have a distribution of effective spectral types.
Yeah, GKM stars.
And
Yeah,
how wrong are they now?
So if you neglect the binaries, they are quite. I mean, they are quite in agreement with the mass range that you would expect.
Okay, so it didn't systematically shift things in such a manner that your sample is not actually representative of the masses that you thought it was.
No.
Okay.
I mean, sometimes you get some very high masses, but that's because there's a binary there. Maybe it's not been detected before, and you just see, I don't know, an emission starting from -10 kilometers per second and going up to 20 kilometers per second, and you get like 5-6 solar mass objects. And you say, yeah, that's a binary for sure.
That's, yeah, but it's a very reliable, I mean, it's a very reliable way to identify unresolved binaries.
Yeah,
That's pretty cool. Is there enough of them to change the circumbinary disk statistics in here?
I don't know. I'm working with some binary people, and they are very excited. I'm like, yeah, I don't know.
Okay. You can count another one who's very excited.
Okay, sorry.
Maybe a quick follow-up on the binary topic. So I think you're also mentioning a project that's analyzing the disk around the higher mass stars.
Yeah.
Any of those you think they are binaries?
Good question. I don't know.
Okay.
The answer is yes, if it's high mass
Exactly.
stars. It's always a binary. Always just say yes,
binary.
is the correct answer.
Even the separation, right, that's pretty good.
Ask
Yeah.
about upper score results. Can you see more about what you find there? Do you find an evolution trend? Do you see more flatter disk or?
So that's quite surprising actually, because I'm seeing like a 0.2 HVR ratio.
Okay, similar
Just-
to younger disks.
Yeah, exactly. There doesn't seem to be a trend, but also, yeah, I mean the upper score. So now there are recent papers, for example, this one from a student of Giovanni Salagna, where basically they are claiming that they can understand better which disks are really part of Upper Scorpius, which are not part of Upper Scorpius, and are part of, for example, of Proteus, which is very close by in the sky, etc. So I think it's a big mess, the Upper Score association right now. But yeah, I don't know. It will become clear. Maybe.
I think Guy already reassigned them.
Yeah.
Yeah.
Okay, because for example in John's paper, I found a lot of discrepancies. Yeah, and he used the Guy assignment.
Well, why are you surprised that the HVR changes? I mean, this is the gas. It's not the dust, right? So
Yeah, I don't know. I'm always looking for trends. So when I saw that it doesn't change that much, I'm still. Why? Yeah, no, actually, that's a good point. I mean, we don't know. Yeah, we don't know. Explored.
When you do this visibility fittings, I assume you just you mentioned you also use some Keplerian mask to clean out or filter out the original data, so that we only fit to this. I mean, how we are dealing with the cloud contamination part
Of the disk.
Yeah, from the data, because I cannot imagine we feed the data that is contaminated by the cloud, right? Even it's in the visibility plan.
Yeah, so I'm filtering it out, checking the image plane. So I first check the image plane and I say, okay, these channels are clearly contaminated. But there are, like, this procedure can be done in different ways. Because, for example, you can also train your, you can also insert some specific terms inside of your likelihood, where, well, basically, while you're fitting it, understand how the different channel maps should look like, okay? And if they differ way more from what they should be looking like, then they automatically neglect those channel maps, okay? But that's, yeah, I don't know, that's a kind of machinery that I didn't want to get my mind on, and maybe for future works, I will insert this sort of tricks in the likelihood evaluation. Otherwise, we have to rely still on the image plane for, you know, excluding contaminated parts. Yeah.
any questions online? Any other questions in the room? Okay, then if not, let's thank the speaker again, and we are going to lunch at the, sorry, let's first thank the speaker. And I just want to say that we are going for lunch at the Student Union, so if you want to join.
And also the speaker schedule is quite empty now. Feel free to sign up for discussions.
Which email was the link in the email?